good afternoon and hello, depending on the time zone. And it's a great pleasure and honor for me to ask you to join our conference. And to start, it's a pleasure for me to give floor to Mr. Alexander Klimov, Rector of the Russian University of Transport. Please, Mr. Klimov.
Dear participants in the conference and forum, dear colleagues, please allow me to welcome you on behalf of the Russian University of Transport at the 6th International Conference of Naval Architecture and Marine Engineering and the 2nd International High-Level Forum on Smart and Autonomous Navigation Technology of Ships. The main purpose of the conference and forum is to exchange ideas, expertise, and methods for solving the conceptual problems of autonomous shipping, to search the optimal ways and directions for the long-term development of autonomous fleet, to shape common vision and approaches that will allow us all of us to move forward on the way to achieve the so urgent goals. The conference and forum are intended to assist in finding innovative solutions that are a synthesis of most modern and most advanced scientific concepts and technologies. The importance of this objective to evidence by the wide range of attendees of the event, which today brings together scientists and developers from universities, academies, and leading enterprises involved in the development of technologies, the introduction, adoption, and operation of autonomous and smart ships, including participants in the International Joint Laboratory of Smart and Autonomous Navigation Technology for Ships. The format of the event is very useful. It was provided by its success last year. I'm pleased to welcome today both newly participating and first-time participants. Opening today's conference and forum, I express my confidence and they will become no less successful. Will offer the estimated colleagues a new opportunity to share their vision of scientific problems, optimal technologies, and algorithms, to exchange their knowledge and expertise, which will certainly give a new incentive to research and our joint effort for the benefit of all the participants. I wish to success to the conference and forum and fruitful and creative work to all the participants. Thank you.
Thank you, Mr. Director. And now I would like to give floor to Mr. Alexander Pinsky from Autonomous Navigation Promotion Center, Marinette Route, please.
Thank you, Evgeny. Good morning, good afternoon, dear colleagues. On behalf of Industry Association Marinette, I'm glad to welcome you at this forum dedicated to the autonomous and smart ship technologies. I want to thank Professor Xia and Key Laboratory on Intelligent Technologies and Marine Equipment Application, and Chairman Wang and the Association of Shipbuilding and Naval Engineers for cooperation in organizing this forum. Also, I very appreciate joint efforts of 3 universities, Russian University of Transport and Rector Klimov, Harbin Engineering University, and Wuhan Technology University, that organized this forum and brought the most portion of speakers for the event. Moreover, this year, these universities established the Joint International Laboratory on Autonomous and Smart Ship Technologies, and this is a very good example of scientific cooperation in our turbulent world. An example how researchers and technologies can cooperate to make our world safer and better. Previously, this laboratory worked in virtual format, but I believe that, and I'm sure that now we will be able to extend this format to more physical and personal cooperation. In Russia, as in many other countries, in the eve of New Year, we make plans and expectations. Our conference, our forum is held just in 1 week before the New Year. And I believe that in the new year, next year, due to a decrease of coronavirus restrictions, we will come to physical joint research projects, joint expeditions, exchange of researchers and students, joint training programs. I believe that we will have new universities from new countries joining the international laboratory. And I believe that this scientific cooperation opens a door for more practical implementation of these technologies, for establishment of links between our technology companies, between vendors and customers of our countries. And such events like today's forum build the solid ground, the solid basement for such practical cooperation and implementation of new technologies. Dear colleagues, I would like to wish a fruitful and interesting conversation today. And taking an opportunity, I would also like to wish you success, prosperity, and good luck in the new year. New developments and new achievements in 2023. Thank you.
Thank you. And now it's time to ask Mr. Wang Junli from the Chinese Society of Naval Architects and Marine Engineers to give an opening speech. Be welcome, Mr. Wang Junli.
好，谢谢主持人啊。这个尊敬的各位来宾、朋友们。 大家上午、下午好。今天非常高兴能够参加第2届国际船舶智能与自主航行技术高端论坛。在此，我代表中国造船工程学会，向与会的各位专家、学者和来宾表示热烈的欢迎和诚挚的问候。 船舶智能化是世界船舶制造业发展的新热点、新机遇和新挑战，已经成为船舶产品发展的一个重要方向。近年来，世界各国高度重视船舶自主航行技术的研究与发展，已经成为 IMO 每次会议讨论的热点问题。本次论坛有利于推动中俄两国在本领域的交流。 合作与共同发展。截止到2022年1月，我国3大造船指标，从完工量是占世界的占有率是42%，新接的订单占世界的48.1%，然后手持订单已经达到了41.9%，稳居世界第一。 中国造船工程学会成立于1943年，是为中国船舶与海洋工程科技工作者服务的公益性、学术性法人社团组织，是发展船舶与海洋工程科技事业的重要社会力量。我会将为世界各国船舶科技工作者的交流与合作发挥桥梁和纽带作用，搭建 共同交流的平台，共同促进船舶科技事业的繁荣和发展，为船舶智能与自主航行技术共同发展做出贡献。最后，预祝本次论坛圆满成功，祝大家工作顺利，身体健康。谢谢。
Distinguished guests and friends. Good morning and afternoon, everyone. Today, we gather online in the early winter to participate in the 2nd International Forum on Ship Intelligence and Autonomous Navigation Technology. On behalf of the Chinese Society of Naval Architects and Marine Engineering, I would like to offer warm welcome and sincere greetings to all the experts, scholars, and guests attending the meeting. Intelligence is a new hot spot, new opportunity and a new challenge for the development of the world's shipbuilding industry, and has become a major direction of ship development. In recent years, countries all over the world attach great importance to the research and development of ship autonomous navigation technology, which has become a hot issue discussed at each IMO meeting. The Summit Forum, sponsored by Russian and Chinese universities, aims to promote exchanges of cooperation and common development between China and Russia in this field. Founded in 1943, the Chinese Society of Naval Architects and Marine Engineering is a public welfare and academic legal persons social organization voluntarily formed by Chinese ship and ocean engineering, scientific and technological workers, and an important social force to develop ship and ocean engineering, science and technology. Hopefully, this forum will act as a bridge and a link connecting ship, science, and technology workers from all over the world, promote the growth and improvement of marine science and technology talents, and contribute to the international exchanges of ship intelligence and autonomous navigation technology. Finally, I hope this forum will be a great success, and I wish you all good health and smooth work. Thank you.
Thank you. And on behalf of the participants and attendees, I would like to sincerely thank all our speakers who made the welcome speeches and opening speeches for their wishes. And I hope that we'll try together to work hard during this conference and forum. And now passing to the working part of our conference, I would like to give floor Ms. Kharchenko Natalia, who is also from the A Navigation Promotion Center, Marinette route. The topic of her presentation is development of mass and mass legislation in Russia. Before giving the floor to Ms. Kharchenko, I would like to remind dear participants and speakers that according to our timetable, we have 15 minutes for presentation. After that, we have about 10 minutes for the session of answers and questions. Thank you. And now, Ms. Kharchenko, please.
Thank you, Mr. Chair. Good morning, everyone. My name is Natalia, and I have a very difficult surname to pronounce, so you may call me just Natalia, that's okay. Within my presentation, I will deliver some interesting topic we have in Russia. Thus, we will discuss current projects we have now. That's not all, I'm not going to speak about all the projects, but the main directions in which we are going to develop and in which we are developing right now. Then I will deliver some slides, some information on mass regulation which we have in Russia currently and which is still under development. I will also deliver some data on mass international regulation in which Russia is particular. And then we will see some probable outcome. The first slide you may see here is current projects, covers current projects in Russia. As I mentioned, we have several directions of project, let's say. Firstly, we initially, at the very beginning, we started to do with autonomous navigation in 2019. At that time, the group of Russian shipping companies, technology enterprises, and universities, under the leadership of Industry Association Marinette, designed the trial project on autonomous shipping. It was a very bright start, and it was like a feel of real startup when the representatives of all these industry entities gathered and decided to start this particular new point in maritime industry. This project, initiated in 2019, was successfully realized even at that time, and several set of navigation equipment were developed, and they were installed on the vessels which you may see in the slides. I'm not going to go deep inside of this project because we have some people in our agenda who will deliver that and who are dealing with that project by themselves, and they will deliver in more details the projects with these vessels, which you can see here on the screen. One more interesting project what we have in Russia is national experiment of autonomous navigation. When we finalized with the trials, and when we saw the results of the trial project initiated by Industry Association Marinette, the results of them were very much interesting, and these results triggered the wide range of development of autonomous shipping in Russia. And our government considered all the benefits the shipping industry in Russia can receive if following these projects. And that's why they started the national experiment of autonomous navigation. And nowadays, we have several vessels which are contracted to be equipped with autonomous navigation systems. And among them, there are 2 railway ferries, and they will manage in 3 possible control regime. They can be fully automatically or under control of the remote control station or by the crew on board. This is a very interesting project, and it is exactly in line is ongoing right now. I would also like to add that these ships are going to get the class of autonomous ships by Russian Register of Shipping, and this will give the new starting point, the new ways to follow the autonomous navigation development. In Russia, we have one more quite interesting and innovative project related to autonomous navigation. This is an autonomous inland ships with electric engines. This project itself, it's at the very initial stage yet. It is under design project, under design stage, let's say. It is assumed that all these ships will travel along rivers, and some of them will travel just here in Moscow, along Moscow River, and they will be equipped with autonomous navigation systems to keep ships on the course and maneuvering. They will be equipped with optical surveillance systems and lidars to be used for safety of maneuvering, and video cameras and internally developed integrated software will be used for automatic berthing. I would like to pay your attention, ladies and gentlemen, that these ships will be not only autonomous, they will be electrical ships, electrical plus autonomous. So this project is going to be very much interesting if it goes quite well. Having so many projects and so many trials and real ships which are already traveling in autonomous or semi-autonomous regime in commercial conditions, our maritime administration considered a lot of issues related to that. And one of those issues is training. As far as autonomous shipping implementation is going further and further, there are needs to have the expert specialists on board and in remote control stations who will be able to deal with that and who will be able to operate mass in most appropriate and most safe way. So Maritime Administration of Russia gathered several maritime academies and universities, and they developed training programs. This training, the list of these training programs you can see on your screen. It is already an ongoing project, and the detailed curriculum already did for that, and we are ready to share within these developments, and we expect that the first experts will be studied already next year. At this slide, you can see the small summary of projects we have now, the timeline within which we follow them, and you can see that we started in 2019, and until 2029 we have a national pilot project. Within that period of time, Russian Register of Shipping developed and approved a set of devices and systems to meet the autonomous navigation. In 2021, there was a national experiments started, which allowed the navigation systems fitting the navigation to be installed on ships and be used in commercial conditions. In this year 2022, the first ships are contracted for a navigation equipment, and training programs are developed and approved by our administration. Next year, we expect several ships to get an autonomy class and introduce autonomous inland water transportations. That is mostly all about our current projects, and now we go to mass regulation in Russia. So actually the implementation of mass really required some interpretations of the current rules and regulations. Thus, in Russia, the mass rules has been developing since 2019, and nowadays we have the whole set of adopted rules and regulations, and among them the government regulation on the national experiment on trials of mass flying the Russian flags, recommendations by the Maritime Authority on application of the COLREG 72 by autonomous ships, rule for mass classification by Russian Maritime Register of Shipping, and professional training standards for specialists of autonomous ships. Actually, we are ready to share mostly all of this data with you, and if you are interested, you may ask us to present these our developments. I also would like to speak about the federal laws. In Russia, we decided that we really need a federal law on legal relations arising from the autonomous ship operation. Nowadays, we have the draft federal law, and it is still ongoing. This document covers mostly all mass-related amendments to several federal laws. It contains mass definitions, remote crew particulars, mass operational requirements and training details, mass documents and certificates, and some other aspects. Currently, this draft federal law is on the second reading in the parliament, and we hope that maybe next year we will get this federal law in full enforcement. When developing all these set of regulations in Russia, we used the functional approach, the so-called functional approach. For us, the functional approach is a principle of complete functional equivalence. By this, we mean that all the functions the crew is prescribed to fulfill on board should be fulfilled irrespective of whether the ship is fully autonomous or semi-autonomous or just partly autonomous. So this functional approach for us is a leading principle on which we base all our regulations developing in relations to mass in Russia. Next step is discussion of international mass regulations. As you may know, mass is on the agenda of the International Maritime Organization since year 2018, year 2019. And rapid development of mass technologies and absence of the regulations was quite a problem, and it was stopping on further development of mass. That's why the Maritime Safety Committee at its 101st session developed and approved the special interim guidelines for mass trials. And the Maritime Safety Committee issued a special circular. The particulars of the circular you may see on the screen. Its document is available for open public. These interim guidelines are subject for further reviews and amendments, and it is on the agenda every time. Within these interim guidelines, there are some general norms explaining on what is mass and how it can be used. These interim guidelines agreed by all member states, which is very important for future development. And these guidelines are foundation for more regulations to be in place later on. In spite of the absence of regulations, mass continued to be developing all the time since 2019. And the International Maritime Organization, responding to this demand, designed and carried out a regulatory scoping exercise to verify whether mass could be used within the existing international instruments or not. This was a huge job done by IMO member states. The three committees of the IMO were involved in that. It's Maritime Safety Committee, Legal Committee, and Facilitation Committee. They did regulatory scoping exercise by themselves and provided the proper reports. The results of the regulatory scoping exercise demonstrated that in general, mass can operate within the existing rules and regulations, but there were several gaps and seams identified which require further interpretations or some additional rules and regulations. Upon the results of this regulatory safety exercise, the necessity of mass code was agreed at IMO level. All three committees considered that actually we need a mass code to be developed and implemented. Thus, the three committees established a joint working group to track the mass development. Maritime Safety Committee, at its turn, established the working group in its last 106th session, and it considered the developments we had within the mass in IMO. For intersessional period, a correspondence working group was established, and nowadays this correspondence working group is doing a lot of job. Mass working group at the 106th session was chaired by the Sweden, and currently operating mass correspondence group is chaired by Marshall Islands. Both groups are now involved in future mass development. Mass corresponding group has already developed the draft structure of the future mass code, and this structure was agreed by the working group and approved by the 106th session of the Maritime Safety Committee. Currently, this corresponding group is dealing with remote control section of the future mass code, communication, navigation, and operational contexts. So all four sections of the future mass code is now on your screen. And any IMO member states who are interested in the development may join this activity within their correspondence group. And just to finalize my short speech, I will introduce just some outcomes we expect from the e-navigation. E-navigation is a rapid developing technology which may bring a lot of positive changes in the maritime industry. We are right at the point of development and implementation of this new technology. Exchange of experience, we think, is a key way to go forward within this direction. Joint international efforts open a wide range for possibilities and further developments. And we do believe that universities are the tremendous platform for researches and developments for the new technologies. Thank you.
Thank you very much, Ms. Karchenko. And now this is time for the questions of attendance. So you are welcome. Please just make note who is speaking. And please, your questions. Please.
那个谁，志林，你给我翻译一下吧，我提个问题，好吧？听到吗？
好的，好的，能听见。
你的报告讲得很好啊，我想问一下，你们未来，我看到了，你们2023年就应该就有自主船了。那么你们确定在哪个航线上进行商业运行吗？哪条航线？
I hear your report. The report is very good. You said the autonomous ship will be on rail in 2023. So which line will you be sailed on the Russia? From which port to from which city to where will the smart ship will be on sale for commercial operation? Which route?
Thank you for your question. I think that Ms. Karchenko will like to answer your question, please.
Thank you, Mr. Chair. We expect that our routes in Barents Sea will be actively engaged in commercial transportations from the next year. And we expect that our two ferries will be fully in line and fully ready to that. We hope that it will be like that. We also have the already ongoing projects, already ongoing ships, ongoing routes with 3 vessels owned by Rosmorport, by Sovcomflot, and by Polarize. So these 3 ships are already in commercial usage, and we expect ferries are going very soon. Thank you.
Thank you.
Thank you. Please, your next questions, please.
Hello. Thank you, Natasha. Thank you for your presentation. My name is Sun Wu. I'm from China Classification Societies. So now you have introduced the autonomous navigation in Russia. So would you please more detail about what it is, the autonomous navigation? What is the system? What is the relation of the system and the officer on ship? Is there any officer or on ship if you are equipped with autonomous navigation and what is the status of the level of the autonomous navigation? Thank you.
Thank you. Thank you.
Thank you, Mr. Chair. Thank you for your question. Currently, we still have some crew on board, but this is a reduced crew. And we expect the ferries which are going to be in service next year. They will have even a master certificate introducing the reduced number of crew on board. But actually, currently, we don't have a fully autonomous ship without crew. We have some crew, and this crew is testing their ability. And actually, one or several ships are managed from the remote control station. That is true. But the truth is also that we still have some crew on board, but this is a reduced number of crew.
Thank you.
Thank you. Next questions, please, if any.
Yes, could you hear me?
Yes, please continue.
Yes, thank you very much for your presentation, and I think it's very good and very experienced and very development on autonomous ship on Mars in Russia. I have a little question for the remote control center, and I saw a slide shows that in Russia they will have some training program for how to say for the future operation for of Mars, and I noticed there is a remote control station a training program relatively. So my question is, what's the interface? I would say the functionality interface between ship and remote control center on shore. So that's my question. Thank you.
Please, thank you for your question, and then Dalia, please.
Thank you, and thank you for your warm words. Actually, we have training programs already in place, as I told, and today, within the day, there is a separate report on this will be delivered, and I think it would be more appropriate to address the questions of training programs to those people who will deliver separate training separate topic on training programs, and it will be delivered by exactly the person who are in charge of that, and they developed this project and have some direct intention to that. The remote control station will also be later on covered by the persons who are dealing with this just from the field, and I think their conclusions and their ideas would be much more interesting for you. Thank you.
Thank you. So as I see, Ms. Natalia gave the general discourse on these topics, but we shall attend other speakers to go on with more details on those topics. So I think that can satisfy the attendees to hear later more details on those topics.
Yes, so, thank you very much. Yeah, thank you.
Thank you, and please. If there are any other questions, please. We don't hear. Sorry. I see on this screen.
I didn't open the microphone. Yeah. Thank you for your presentation. I have a question. Can we have your adopted regulations for the Mars in detail? I mean the materials or the documents.
Yes, please.
I'm sorry, I can't really understand. I can't get what your question is. Do you wish to get any of our legislative documents? Is that the question?
Yes. You mentioned you have got the adopt regulations for mass since 2019, and I'm very interested. All your regulations has adopted, and so if okay, we'd like to read your documents. That's my point. Yes. Okay.
Yes, thank you. Thank you for your clarification. We have our regulation adopted all except the draft federal law, because federal law is still draft. But we are ready to share these documents with you, and I think I may give your contacts, may get your contacts, and we will definitely send these documents to you by email or whatever is convenient for you.
Do you mean all the regulations are in the stage of draft?
Only the federal law is still draft, but regulation on call reg interpretations and usage by mass, then classification requirements for mass, and regulation of our maritime authorities regarding the experiment is all adopted, and it's an operational in-service document, and we may share these documents with you. We may also send you our draft federal law, and it is this draft law is already in the good stage of development, and we still have some issues to be discussed and developed, because you know Russia is a very big country, and there are a lot of persons who are interested to add something in the draft law. Moreover, this draft law is already in the parliament in the second reading, but I don't know how in China, but in Russia, if you put something into parliament, it doesn't really mean that you are getting back exact the document you submitted. So we have a lot of job with that, but it is already in very good stage of readiness. So we may send you all the documents which are already approved, and we may send you a draft federal law as well.
Thank you very much. Okay, that's good. Thank you.
Thank you. Thank you very much. Thank you for your questions, and Ms. Natalia, for your answers. And please allow me to go to the next point on our agenda. And we invite Mr. Zhang Baozhen from China Institute of Navigation to take floor on the topic of progress in research and development and testing of MAS in China. Please, the floor is yours.
Okay, can you see my PPT?
Yes, yes, but it's not full screen. We can
Yes,
see.
okay.
Mhm.
Yes. So this is the first one. Okay, thank you, Chairman. Distinguished guests for this forum. My name is Zhang Baochen from the China Institute of Navigation. I'm the vice president, and I'm also the senior vice president of the International Association of Institutes of Navigation. So I'm very glad to give the presentation for the progress in mass research and trial in China So I like to say thanks to Mr. Professor Xia Guihua. Mr. Xia invited me to give this presentation in this forum. So now I start my presentation. I will give you 5 points for my presentation. So now I'd like to go to the first part, that is the overview of early research related to math in China. The first point is that the rules for intelligent shapes 2015 issued by China Classification Society. And you can get it openly, so I don't want to waste your time for this point. And the second point is the special project Intelligent Shapes 1.0. This project launched by the Ministry of Industry and Information Technology in 2016. And this project takes decision-making assistance as the research content. And the assisted driving system developed by Highland and other institutes is integrated into the sea vessel Dazhi. It is a very famous shape. And the third point is the safety assisted driving system project. In view of the characteristics of ferry navigation and environment in the lower reaches of the Yangtze River, Wuhan University of Technology started the research and development of a safety driver assistance system in 2017. And the results were installed in the 78-meter long Banxin 2 the following year. And the fourth point is the research on the development mode of unmanned transport ships and their impact on the shaping industry to predict the impact of intelligent navigation technology on shaping industry in the middle of this century. China Waterborne Transport Research Institute, WTI, carried out this research in 2017 and proposed that the original architecture of intelligent shaping system and revealed that the intelligent shape are the core element of the system. And the fifth point is the intelligent navigation system experimental platform. In 2018, WTI cooperated with the CSSC 704 Research Institute and Navigation Brilliance Technology Company Limited to develop a remote driving and autonomous navigation technology test platform. And the results were integrated in the 21-meter long Zhiteng and successfully demonstrated in Qingdao on May 16th of the following year. And the last point is that intelligent navigation system experimental project. In 2019, Zhuhai Yunzhou Intelligence Technology Company Limited, WUT and the CCS jointly carried out the project. And the results were integrated in the 13-meter long Jindouyun Zero and successfully demonstrated in Zhuhai, Guangdong on December 15th. That's all for the first part. And now let's go to the second part, basic information of the math project of the National Key R&D program. The first one is the project source. According to the recommendation of the Ministry of Transport, the Ministry of Science and Technology has established the project of key technologies of intelligent navigation and control of ships based on ship-shore coordination. TINCONSBIRSC for short, in the National Key Research and Development Program in 2019. The project budget is about 84 million yuan, and its financial allocation is about 25 million yuan. And the implementation period is 3 years. And this project was completed in the end of last year. And the objectives of the project, it focuses on solving key technical problems such as ship intelligent navigation and control coordination theory, ship navigation intelligent perception, and ship autonomous collision avoidance, and establish a testing system, laying the foundation for China to take the lead in building ship intelligent navigation and control system based on ship-shore coordination, enhancing the core competitiveness of intelligent shipping technology, innovation, and industrialization, and serving intelligent shipping development strategy. And the third point is the task commitment. The project was led by WTI. I used to be the chief scientist of the project. There are 5 subjects in the project, and the named person in charge, lead and participating units of these subjectives are shown in the following table. Since the time is limited, I don't want to introduce it in details. So now let's go to the third part, the main technical achievements of the project. The project has been completed last year and passed the comprehensive performance evaluation organized by the Ministry of Science and Technology. Through 3 years of research, the project has broken through a series of key technologies, developed 11 systems, 5 platforms, and 2 sets of equipment, established an intelligent navigation test field, formed a series of standards and specifications, successfully carried out the demonstration applications of intelligent navigation systems on inland ferry and container ship in the typical section of the Yangtze River trunk line and Changhusen route, and on 316 TEU container ship in the coastal areas of Qingdao. The following, I will share the main technical achievements for the sea vessels. The first point, the Intelligent Navigation System, INS, for sea vessels. The systems consist of 5 subsystems: navigation, environment, and situation awareness system, remote control driving system, and a shore-based monitoring platform, route planning and autonomous collision avoidance system, automatic berthing and unberthing system, and the last one is advanced driving assistance system. The first point is in navigation, the nexus through the analysis of the perception needs for each driving mode of intelligent navigation. The design scheme of NASA's based on marine radar, AI's LiDAR, and infrared visible light and other technologies and equipment. A maritime target recognition algorithms based on deep learning is developed, and the related equipment and systems are integrated. Experiment and debugged to realize the collection, fusion, and automatic detection, identification, and the tracking of real-time information of the shapes, navigation, environment, and the situation, as well as three-dimensional comprehensive reconstruction of navigation, environment, and the situation in various ways, such as radar signal enhancement and AR. The second, remote control driving system, RCDS, and the shore-based monitoring platform. The general instruction set for shape, RCD, and intelligent navigation monitoring requirements is compiled, and the highly reliable transmission of shape, shore perception information, service information, and remote control demands is realized according to the design scheme proposed by the research, a shore-based remote control platform that takes into account the needs of shape-based remote driving, shape owner supervision, and the government governance is developed so as to realize the remote control driving and monitoring of coastal and inland shapes by shore. And then the route planning and autonomous collision avoidance, ACAS, that we have finished the, we have realized the integration and expression of shape navigation dynamic information and shore-based service information on electronic tracks based on the multi-objectives optimization methods of complex constraints. The whole process optimization algorithms and response model of shape route are developed. And the dynamic optimization of routes based on shore-based service information is realized. Using the constructed collision risk judgment model, encounter situation analysis model, and collision avoidance decision model, and efficient algorithms for autonomous collision avoidance of shapes based on CORAL. And the type scale of the demonstration shape was developed and realized the avoidance operation of various situations such as encounter, overtake, and cross encounter, etc. And the automatic berthing and unberthing system. This system is combined with the dynamic positioning system. And I don't want to take your time for it. And the last one is advanced driving assistance system, ADAS, based on the perception system, route autonomous planning software, collision avoidance software, and advanced assistance system that can provide drivers with traffic conditions, safety risks, and collision avoidance suggestions through text, graphics, color, sound, and other ways in the world development, which reduces the labor intensity of the driver in the manual driving mode of GFA and provides conditions for the comparative study of manned and unmanned driving. So now the second point of the third part, intelligent navigation support technology and system. The first, intelligent navigation shore-based information support technology. On the basis of an all-round analysis of the needs and characteristics of intelligent navigation information services for coastal, inland, and ocean-going vessels, a list of information services in 13 categories and 64 subcategories, including traffic organization, navigation assistance, and maritime safety, was proposed, and data standard guidelines were compiled for key information categories. And the protocol on amendments of maritime service for MAS was submitted to the International Association of Marine Aids to Navigation and Lighthouses Authorities through the China Maritime Safety Administration. And the second, technology and the system for global intelligent navigation communication. In view of the fact that the current maritime communication systems cannot independently meet the needs of global communication for ship intelligent navigation, a global-oriented intelligent navigation communication network scheme is proposed. A technical assess priority scheduling mechanisms for different navigation areas, different driving modes, and multitasks is constructed. A multi-network and multi-mode adaptive shape-shore fusion communication equipment is developed, and the communication system of Qingdao Mass Test and Experiment Site is built to realize the automatic selection and switching of various communication modes, such as microwave, 5G, satellite, and so on. And the last part is that intelligent navigation network security technology and system. And I like to pass this part. And the third part, third point for the third part, intelligent navigation testing technology, system, and evaluation methods. Test methods and systems of intelligent navigation according to the test requirements of different scenarios and driving modes of intelligent navigation. The test content and the methods are clarified, which covers 3 functions of perception, decision-making, and control, 3 options of navigation, anchoring, and berthing, unberthing, 4 driving modes of assisting, remote control, autonomous, and automatic berthing, unberthing. Test technical guidelines are compiled. Virtual test platform is developed, supporting command center and the test communication network environment were built in Qingdao Mass Test and Experiment Site. And the real ship tests were carried out. And the second, technical level evaluation method of INS, based on the classification research of shape intelligent navigation driving modes and the analysis of a typical R&D cases home and abroad, combined with the design, research, and development, testing, verification, and demonstration application of Zhifei and its INS and technical levels that are integrated with the IMO mass degree classification method and can more deeply reflect the technical level of INS are proposed. A qualitative plus quantitative technical level evaluation method of INS proposed from the two dimensions of safety and performance. A standard formed for INS evaluation, named as the SHAPE Autonomous Navigation System Technical Evaluation, has been issued by China Institute of Navigation. So that's all for the third part. Now let's go to the fourth part, intelligent navigation. Test, trial, and evaluation of GFA. The 5 intelligent navigation subsystems of the sea vessel are integrated and installed on MV GFA, forming a comprehensive intelligent navigation system, integrating assisted remote control, autonomous driving modes, and automatic berthing unberthing. The main technical parameter, the particulars of GFA are shown in the table. And I'd like to save the time for the meeting. And from October 2021 to April 22nd, 2022, GFA has carried out more than 80 times intelligent navigation trial, test, and verification activities at the Qingdao mass test and experiment site, with a cumulative time of more than 300 hours and a voyage of nearly 1,000 nautical miles, 20 times of remote control driving, 80 times of autonomous driving, 40 times of automatic berthing, unberthing, maintaining a successful record. And since 22nd April 2022, GFA has been engaged in commercial operations between the 3 ports of Qingdao, Dongjiakou, and Rizhao, and maintained more than 200 times intelligent navigation experiments with a cumulative experiment voyage of more than 12,000 nautical miles and a sailing time of 1,500 hours, including 25 times of remote control driving, 30 times of automatic berthing, unberthing. The ACAS has always maintained the generation of auxiliary decision-making suggestions. In March this year, China Institute of Navigation evaluated the technical level of the INS of GFA according to TCIN 003 to 2021, and concluded that the remote control driving system was advanced and the autonomous navigation system was immediate. So now let's go to the 5th part, main research gains. There are 3 parts of the contents of this part. The first one, the preliminary study on the coordination theory of intelligent navigation and control of ships. We have got the concept of the coordination theory, and we got 4 conclusions for the coordination in the study. And the second
Sorry, there is no sound on our part.
Yes, yes, now.
Yes, now it's okay. Thanks.
The second for the part 5. This point is the ship-shore coordination is the correct technical route. There are 2 points. The first one is the perception, decision-making, and the control process of intelligent navigation are inseparable from ship-shore coordination. The second, as information technology factors evolve into important intelligent navigation safety risks, it is important to strengthen risk governance from the 3 spaces of physics, cyber, and the rules. And it is difficult to achieve effective governance of intelligent navigation without ship-shore coordination. And then the third point for the part 5, the existing maritime communication conditions are not the fundamental obstacles restricting the intelligent navigation of ships. Project research and actual ship test results show that first, space-based communication, such as VSAT, Asia Pacific 6D, 5th generation maritime satellite, or other low orbit communication satellites can meet the needs of global communication for ship intelligent navigation. And the second point is that the shore-based communication systems based on low frequency of 5G and over the horizon microwaves may meet the needs of intelligent navigation communication within 25 kilometers along the coast. So now the last part for my conclusion. The first part is the achievements of advanced driving assistance system of the project are very mature and can be widely applied and promoted. And the second point is that the promotion and application of remote driving technology achievements is subject to 2 conditions. The first one, regulations clarify the roles and responsibilities of officers on board and shore-based operators, but China has not yet completed relevant legislation up to now. And the second point is the perception system should be highly credible. The perception system of Zhifei can now be applied full-time during the day, and its reliability at night and in rain, snow weather conditions is to be further improved and verified. At this stage, the promotion and application strategy of the RCDS achievement achieved in this project should be conditional on having a competent crew on board, and she can take over the operation and the control of the ship when necessary. And the third point, that the ACAS of the project has realized the collision avoidance of multiple ships. And our test shows that 5 ships in the situation can be solved, but has not yet achieved a high level of unity of safety, efficiency, and economy. And the common laws of collision avoidance models for different shape scales needs to be explored and summarized through a large number of experiments. Coupled with the limitations of perception technology, or whether autonomous navigation technology still has a long way to go. The current application strategy of autonomous navigation technology is to expand the frequency of tests in open waters and gradually increase data accumulation. In short, the application of intelligent navigation technology at this stage can only select different driving modes, including switching from intelligent mode to manual mode, according to the navigation tasks and environment complexity. In other words, relying on multiple driving modes to achieve a complete voyage is an inevitable choice in the early stage of the development of intelligent navigation technology. Without this process, unmanned navigation technology will never mature. Before I finish my presentation, I'd like to give you the information about the first World Conference on Maritime Science and Technology. It will be held in October next year in Qingdao. Its theme and the main topics are intelligent shipping. All you are welcome to participate. The Congress and the speeches are also welcome. Meanwhile, the first meeting of International Alliance of Port and Shipping Science and Technology will be held the same place, and during that time, relevant organizations are welcome to participate the alliance and the meeting. That's all for my presentation. Thank you.
Thank you very much. It was very great interest and very condensed. And thank you also for the invitation extended to the attendees of our today's meeting to participate in the next World Conference on Maritime Science and Technology. Thank you very much. And I would like to ask the attendees if there are any questions, please. Please, a question from our part, Mr. Yukonchikov.
Good day. Dear Jan, thanks for detailing the report. I'm glad we're on the same path. The questions is a bit different. Are your developments in China centralized within the state, or are they carried out by independent teams? Maybe competition? Thank you.
那个谁能帮助翻译一下吗？我没有听太清楚他说的。
我想他问的问题就是说，我们这个技术的这个研发是在我们这个国内自主研究的吗？还是雇佣了一些这个第三方的这个团队来帮助我们进行这个技术研发？
Oh, okay. Thank you for your question. All the research and the development completed by independently by university, company, and institutes in China. There's no foreign help for the object, the project.
Thank you very much. You also have a question, please, Natalie.
Thank you. Thank you for the presentation. It was very nice, interesting, and comprehensive. And I have just two questions about those who were involved in this project. whether any shipping companies participated in this project, and which of them were participated and in what way? Thank you.
Oh, yes. There are more than 20 units participate in the project. There were 4 universities, Dalian Maritime University, Harbin Engineering University, Beijing Jiaotong University, and also Wuhan Technology University. And there are many institutes belongs to the CSSC and coastal shipping. And also there are several institutes belongs to the Ministry of Transport, WTI for example, and also all the navigation support centers, Beihai, Donghai, Nanhai navigation support centers, all they participate this project.
Thank you. Thank you very much for your answer. Please, any other questions, please? I'm sorry, I don't see, I don't hear any questions. So thank you very much once again for your brilliant report, and allow me to ask our other speaker, Mr. Teterev from Rosmorport, to take floor. Thank you once again, and Mr. Teterev, your floor is the floor is yours, please.
Okay.
Mr. John, please, can you remove your presentation? Yeah.
Yes.
Thank you. Thank you very much, sir.
Okay. My picture on the screen or not?
Yes, yes.
Just a moment, please.
Yes.
Okay. Oh, it's okay. Thank you. Thank you.
Dear colleagues, please let me know my presentation on the screen or not.
Yes, it's on the screen. Thank you.
Okay, let's start. Good afternoon, dear colleagues. My name is Vladimir Teterev. I represent Federal State Unitary Enterprise Rosmorport. Rosmorport is a state-owned company responsible for development of Russian merchant marine port infrastructure. The company maintains the depth of ports equatories, provides building and operating of berths, shipping channels, coastal and floating heights of navigation, GMDSS coastal radio stations, system of vessel traffic service. At the same time, Rosmorport is largest ship owner. Our company operates about 300 vessels, including 37 icebreakers and other types of ships. It means tugs, dredgers, rolling cargo, and so on and so on. We consider autonomous navigation technology as a many promising technology of the nearest future. We expect that this technology can be a key of reducing the risk of navigation and our fleet operating costs. It is why we are taking part in testing autonomous navigation systems and are trying to solve the following tasks: creation of new ship and show hardware and software for remote and autonomous fleet operation. Broadband ship-to-shore data transmission via WiMAX, 5G, VSAT. And by the way, Rosmorport is owner of WiMAX network in east part of Gulf of Finland. The next task, big data processing, including cloud technologies and artificial intelligence. We have a number of aims of the project. Some of them to get the experience in the creation and operation of autonomous vessels, to take a part into national legal regulations preparation for the operation of autonomous vessels, to construct the shore infrastructure for autonomous navigations, trainings of specialists for the operation and management of autonomous vessels. We have started with remote and autonomous navigation experiments with 2 small dimensions vessels at 2019. There are the Dredger Redut and SCO Рабочая. Remote control unit had been installed on board of the Dredger Redut. In autonomous mode, SCO Рабочая can move according to the road given by navigator and without navigator's help to provide the divergence with other vessels. Divergence algorithms are offered by several Russian universities and companies now. At the beginning, we have a number of problems, and main of them was providing a reliable broadband data transmission channel between the dredger and the SCO. And of course, now you can see that we have done the first step only. The next step will be installation on board of RoRo vessel Marshal Rokossovsky autonomous navigation system. Motor vessel Marshal Rokossovsky is a modern vessel with a high level of automation and twin fuel engine with the ability to run on diesel and natural liquid gas. The ship operates in the Baltic Sea between the ports of Ust-Luga and Baltiysk. And we are going to start operation in autonomous mode on the middle of next year. We are in process of designing for the installation of remote control and autonomous navigation facilities on board motor vessel Marshal Rokossovsky now. The remote control center will be established in St. Petersburg on next year. In the same time, motor vessel Marshal Rokossovsky will be equipped with software and hardware so that it will be able to provide 3 modes of ship's navigation in Baltic Sea. The first, the mode of navigation's assistance for the crew. It means that the new facilities will be able to provide the navigation advices to the ship's mate on the bridge. The second, the mode of remote control of the ship from the center in St. Petersburg. The third, autonomous navigation mode. It will be done possible the navigation on deep sea without participation of crew member at all. It is all my short presentation. Thank you for your attention. Thank you.
Thank you very much. Nevertheless, that the presentation was short, I think that it gives place for the questions, probably. So I ask our esteemed participants and attendees to ask the questions if there are any, please. I don't hear the questions. Mr. Teterov, thank you very much for your presentation. And I think there are a few questions because this topic has already been discussed in the presentation of Ms. Harchenko also, and so it was a very good demonstration of the current situation of the implementation of the project. So we thank you.
Thank you very much. Bye.
Thank you very much. Thank you. And now, please, dear participants, I would like to offer floor Mr. Sun Wu from China Classification Society. The topic of his presentation will be on the China's autonomous ship regulations and the regulations construction. Please, the floor is yours. Yes, we see your presentation. Thank you. Please, it was seen, yes, but now it's the screen, not full screen now, but it was full screen previously, just a few moments ago.
Sorry, I mute the microphone. Okay, yeah. Okay.
Oh, it's okay. Thank you. Thank you.
Good afternoon, everyone. So I'm very honorable to share the experience or the rules for intelligent ships in China. So in Europe or American, we also call it smart ships, but in IMO, we call autonomous ships. But in China, we call intelligent ship. So we introduce 4 parts. The first one is about CCS rules. The second, I will introduce the interim code for trial and survey of autonomous ships. This interim guide is the code of the China Maritime Safety Administration. The third will introduce the participation in development of IMO mass codes. Just now, Ms. Natania have introduced, so I will short it. Then the last one will introduce the practice of China. The first, as you, all the participants in China know that in 2015, CCS has issued the first version of rules for intelligent ships. This rules is based on the concept of intelligentization. This rules is mainly focused on functions and systems, and also the definition of intelligent ship is given. The intelligent ships are those ships which are equipped with intelligent systems to achieve intelligent operation on ship navigation, maintenance, and cargo operation of the ship, etc., to ensure safe, secure, environmentally sound, and efficient operation of ship. Intelligent functions covers decision support, fault diagnosis, operation optimization, and autonomous operation, etc. Through the technology, including big data, artificial intelligence technology. These rules also propose a 1+M model. The 1 means a ship has an integrated digital platform. The N means there are many functions. So we call it smart functions or intelligent functions. So in these rules, we use different class rotations to to express the functions. This is the 1+M model. So in the ship, there are integrated digital platform. It covers the perception, analysis, or communication, etc. Then based on the platform, we have different applications. So we call different intelligent application functions. There covers navigation, machinery, energy efficiency, how maintenance or cargo handling or cargo management, also covering the remote control. So in these rules, we also propose the trend of development based on the first is the way of intelligentization. We think the machine will replace human gradually. The application objects. So we think the technology will evolve gradually. The intelligent functions will occur on a single system first, then to single scenario, then multiple systems, or up to whole ship. And the functions, according to our understandings, the first is digitalization, then the integration of the information, then provide decision support, then the ship-shore interaction, exchange the information between the ship and the shore. Then they provide partial autonomy or semi-autonomy, that there are a human provide surveillance on board ship or on shore. Then up to the full autonomous. According to our understandings, the full autonomy, we think if the ship achieves full autonomy, there is also still lead a shore center to monitoring the ship, or and provide some input or some information or some the operation to the ship in some emergency situation. Then we are introduced CCS guidelines for unmanned cargo ship. So in 2017, China Unmanned Cargo Ship Alliance was established. So through this alliance, we also conducted analysis or the working or works about how to construct international voyage, a cargo ship for international voyage. The first is model building for an 68,000 DWT unmanned bulk carrier. It is international voyage. The second, we have conducted a risk assessment. The third, we carry out scoping identification on the safety and the pollution prevention requirement for unmanned ships. This picture shows the model for unmanned cargo ship. So we covers the communication or electrical systems. The main parts is the autonomous navigation systems, just introduced by a Russian colleague about the autonomous navigation. The second is about the source, the safety systems, or the hull safety, or the ballast systems, or the cargo and others. Also covers the firefighting or pollution prevention, or some emergency situations also considered in this model and in the risk assessment. So we also carry out the risk assessment for unmanned cargo ships. So we provide accepted criteria. Then we define the scope of risk assessment. Then we carry out risk identification, hazard identification and analysis, risk and provide risk mitigation and control measures. Finally, we have identified requirements for subsystems. Based on the process of the risk assessment, we developed the guidelines for the unmanned cargo ships. The guidelines is mostly focused on the measures, the risk mitigation measures. So these slides will show the contents of the guidelines for unmanned cargo ships. So we have based on the risk assessment and according to goal-based standard to make these guidelines. So there are situation awareness, navigation control, and machinery installations, the mooring and anchoring. There are some another that also cover the shore control centers or security and cybersecurity. So we have found that the environment protections or if unmanned cargo ships shall comply with all the existing measures for the environmental protection. This guidelines was issued in 2018. The title was changed to Guidelines for Autonomous Cargo Ships. The CCS rules systems for intelligent ships. So in 2020, so we have combined the rules for intelligent ships and the guidelines for autonomous cargo ships. Now we're considering the experience gained from the industries, also the development of the technology in the world, also the discussion occurred in IMO. So we developing the rules for intelligent ships 2020. So we have developed another guidelines for how to application of the rules for intelligent ships. So we have achieved one rules plus multiple guidelines. The guidelines also covers the basic applications or basic requirements. For examples, the cybersecurity, also the software reliability, how to approve the software. So this is the basic requirements. Then we also have some specific application guidelines. For examples, we have the guidelines for energy efficiency, guidelines for the intelligent machinery, guidelines for the integrated digital platform, etc. So our rules covers the whole process of the ship, from design, proving, construction, and the survey and the certification, all the process. So CCS rules has has many class rotations. After 7 years of development, now we have more than 8 class rotations for intelligent ships. So we have AI, means autonomous operation. it is not only just the autonomous navigation, it covers the whole operation of the ship. And RI, remote control. So the I means we have a different degree. The NX is about navigation. The H, the whole maintenance. M means machinery. EX means energy management. The X means a different application field or different degrees. The CX means cargo handling, and I were integrated digital platform. In those years, we also developed some new requirements for Dragon and all the intelligent management for science research. And in the future, we also developed other notations for the inland water ships. And also the functions for tax, etc. Next, we will introduce the interim code for trial and the survey of autonomous ships. So, on behalf of the China Maritime Safety Administrations, CCS has developed these guidelines. These guidelines cover the 5 chapters. The first one is general, the second is application, and the third is autonomous navigation, the chapter 4, remote control, and the chapter 5, process of trial. So this code is mainly focused on the safety of autonomous navigation and remote control navigation. So we also call it remote driving of ship. So the government issued these guidelines in the next quarter of next year, first quarter of next year, maybe. So now is just the draft. China and the CCS also actively participating the development of IMO mass code. Just now, Ms. Natalia introduced the whole process of the IMO has done for developing the mass code. So China also CCS as on behalf of China, a maritime administration be responsible for the regulatory scoping assess on SOLAS Chapter 5, the safety of navigation as a leading member state. And we also actively participate in the development of the mass code and the correspondence group. So now we are responsible for development of section 3.3 communication of mass code as leading member states and cooperate with Turkey, and also contributing to the development of section 3.1 navigation, section 3.2 remote operation, and section 2.1 operational context as supporting member state. For the operation context, we cooperate with Russia federations. We can provide support and provide our opinion, our understanding to Russia. Last, we introduced the practices of China. So just now, Mr. Zhang Baochen has introduced the many projects or the process of development of the intelligent ship or smart ships in China. So our some sensors about the ships from CCS expertise or experience were introduced in some numbers in the past 7 years. Now more than 200 ships have passed CCS drawing approval. More than 200 intelligent ships have passed CCS drawing approval survey and certification and obtained the classification of intelligent ships. The ship types not only cover bulk carry, tank, and container ship, but also include LNG ships, polar ice breaking research ships, PCTC, and others. And more than, according to our more than 18 models of intelligent systems obtained approved or type approved CCS. So there is a next pilot project. Zhou Haiyun is the first ship which obtained the CCS classification of autonomous navigation in open sea. So it's also called open water, and the remote control functions. The ship was delivered on October 31st, 2022. So that's all for my introductions. Thank you.
Thank you very much. I see that your contacts are now on the screen. Dear participants, do you have any questions to ask, or maybe ask for the comments, please? Mr. Yakunchikov, please.
Thank you. Thank you, Mr. Sun Wu, for the report. The legal issues are very important. Do you see the Chinese Maritime Social in IMO, interacting with IMO, International Marine Organization? Tell me, sending them test reports and so on in IMO from Chinese Marine Organization. Thank you.
I'm sorry, I'm not clear about your questions. Please repeat. Thank you.
So I asked our colleague, he asks whether your organization sent the tests, the results of of the navals to International Maritime Organization. That's what the question is.
Yes, thank you. So, but in China, now Mr. Zhang Baochen has introduced all the projects. So China also sent a test, a submission to IMO or IMO for the mass trials in China, Jingdoyun 0. This is already sent to the IMO, but another testing, the report or testing the trial of mass, they were decided by the ship owner. So in my understandings, the government or the China Maritime Safety Administration will discuss with the ship owner, decide if their report, the record or outcome of the trial to IMO or not. Thank you.
Thank you very much. Thank you. Dear colleagues, any other questions, please? So I would like to thank you sincerely, our speaker, once again for his very interesting report. And I think everybody has got much new information from it, and so we need time to understand and to comprehend the information. So there are no questions just now on the spot. Thank you very much. And now I would like to give floor to our colleague from Brazil, Mr. Sorry. So there is some replacement of the speakers. They told me just now, so I'm sorry. Can I now offer floor to Ms. Li Xin from Shanghai Merchant Ship Design and Research Institute, if it is possible now, because the speaker who was programmed for now, he asked to use another time slot. So can I ask Mr. Li Xin from Shanghai Merchant Ship Design Research Institute to take floor just now with his topic on some studies and considerations on mass design? Is it possible? Please. Mr. Li Xin.
Yes, thank you, Chair. Let me have the floor.
Thank you very much to you for your understanding. Thank you.
So may I share my screen?
Yes, please.
Yeah, okay, thank you. So, okay, thank you very much, ladies and gentlemen. It's my honor to be here to share my some studies and the considerations on mass design. My name is Li Xin, and I'm with the Shanghai Merchant Ship Design and Research Institute of CSSC Group, and my company. So actually it's focused on merchant ship design, and I was focused on ship type R&D and mass research and AI solution application for at least, I think, totally for at least for 20 years. So my presentation will have three parts. One part is about the mass and from the aspect of a ship designer, and the second is the to share our thinking about the element affecting the mass design, and of course the last part is the development of mass design, which we have some practice in it. And the first I will share my idea very quickly about mass. So actually not only IMO, I think all over the world are talking about what's the mass, but I think in IMO, it seems the definition or maybe the terminology will cover the definition of mass. But in my opinion, as a ship designer, we found some features of mass. The first is the mass will be the digital and the connected, and wherever the on board or the ship and shore. So the ship is digital ship, and of course it well connected with the shipping company on shore and management and authorities. So I think this is the main feature of the first feature of the mass. And the second is the mass will operated by, I would say, smart decision. So I would say maybe we have crews on board to control the vessel, but the crew will have some, for example, a smart decision-making support for giving device to operate the vessel better. And of course, the third feature is the automated in various levels. For example, just I would say that in the afternoon, in the past 2 hours, we are talking about a lot of autonomous navigation. So in this level, so the vessel will be automated or automatic operation in, I would say, in various levels, but well, according to the device by, I would say, the collision avoidance AI solution. So that's the third feature of the MAS. But I think the last feature and I think the main feature of the MAS is to have say to safer, greener, and more efficient than conventional ship. And of course is in the mass correspondence group, we have some idea on the safety level. So at least the MAS at least has the same, I would say, same level, same safety level as the conventional vessel. So that's why we develop the MAS, not just because of the novel technology. This is our the idea for how's the level of autonomy. So we have this is the 4 levels is according to the in the aspect of technology or technical. It's totally different with the degree of autonomy in IMO, especially in the RSC regulatory scoping exercise. So the level 1 that we call decision assistance, and then partial autonomy, and then the system will do more, and the human will step behind it. So at the level 5, we will have the full autonomy vessel. But I think in the future, not only the 4 or 2 years later, or maybe 50 years later, all those the various level of autonomous ship or MAS will be sailing at the same time in the ocean. And the third part is the element affecting MAS design. So I will go quickly for this project. I think the first is the rules and regulatories. I think Mr. Sun Wu and I think a lot of gentlemen get involved in the MAS code discussion in IMO. So obviously this is the main effect element affect the MAS design. And the second is cybersecurity. Why I put this element on this, because this is a lot of requirement for cybersecurity, or higher requirement for cybersecurity is from the shipping company. So I would say no one like shipping company on the earth cares about their data or their security, cybersecurity. So this is sometimes when we in the last 2 or 3 years, when we design some smart ship or MAS, the owner will sometimes give our cybersecurity special requirements, which will affect the system on board and system design on board. And of course, the risk assessment will have a great impact on the system on board. Not only the MAS system, but also every system which will have connected outside. And the third is remote control. I think this is will impact the system design on the vessel, and of course they will have some I would say the functionalities on board. And of course, they will test their verification. And meanwhile, as of today, so the test and the verification is still developing, and I would say the steps, the standards, and the procedures and sometimes rules cover it. So it's still on developing, but this is have a great impact on the mass design and the mass building and also mass system design. And the third is development of mass design. In this part, I will share some our experience or ideas for the mass. So according to the level of autonomy in the previous slides, so the level 1 and the level 5, the vessel will have huge change. So this will give the various type of merchant ship, different different changes. For example, the level 1 and the level 2 for bulk carrier or container vessel, they were totally different general arrangement. And of course, the design criteria for the cargo hold, cargo area, and the engine room. So this is quite different. It's a totally different story. And we have some experience on the level 2 or level 3 mass. This is I would say a scientific research and training ship for Dalian Maritime University. There are lots of smart functionalities on board, including remote control and intelligent ship navigation. And so actually, this vessel is not only a smart ship, but also is a lab for mass system research in the sea. So sometimes the vessel will be as a demonstration or testing vessel. On board, it will go outside for testing the mass system, various functionalities. And of course, the third is the training for the navigation student for the future operation, mass operation. And for level 4 and level 5 mass is quite different. Will have obviously a great changes you can see from the outside against the conventional ship, like the general layout, the control mode, and I would say the emission and the systems on board. And we have some this is level 4. This is a level 4. I say the level 4 container vessel, autonomous ship. There is no crews on board. We have finished the basic design on this vessel, and not only we on this vessel, not only the autonomous functionalities on board, and of course we applied lots of green technology on board. So this is not only green but also is smart, and it's a totally I would say we make the concept from the different ground, comparing with the conventional vessel design. So this is all the aspect, all the directions we when we develop this vessel, like the GA layout, like the control mode, like the communication, like the power, and of course the sensors, and of course the safety system. So there are different directions. So that's why when we face a autonomous ship or mass, when we design it, so we will have different, quite different, I would say quite different directions we have to think about deeply. And of course, for the first, we have to figure out the functionality on board, what's the functions those vessel will have, and classification and the classification notation and the standards or specification or some key parameters, which is I would say is valuable for the shipping company or the operator, and of course the core system selection. So on this direction, so we will spread our, I would say, our ship design as the conventional, we will have overall performance study and design and how design and machinery design, and of course they have a very important design for the system architecture. So we will design the whole framework of the vessel, not only mass system, but as we know, the mass system is actually part of a system on board. So it's a part of system of systems on board. So we have to, as a ship designer, we will put it as a part of the vessel, and then we will figure out all the requirements for all the system of different parts. So it's quite different for the mass design because it has a great functionalities on mass operation. So, and this mass operation will impact the ship layout and the ship system design. So I think this is this will get mature according to I would say with the development of the mass. So I think this is our this is my I would say my sharing with the study and the consideration on mass design. So I hope this is helpful. Thank you. Thank you very much.
Thank you. Thank you very much for your presentation. And dear participants, please, your questions and comments are welcome, please. Dear participants, please. Wait. From my part, while the attendees are preparing their questions, I think I would like to highlight a very systematic approach that you demonstrated. And everything is very logical, and I think that these materials can be a very practical basis for the research. It is very systemized and very logic. Please, Mr. Yukunchikov.
Thank you. Tell me, please, you participated in the development of GFA modern China ships in autonomous navigation. Thank you.
I'm sorry, so I didn't catch you very clearly. Is you asking the what how many vessels or how many mass have designed in China, or I don't know.
Shall I comment on the question? Mr. Yukunchikov would like to ask whether your research institute participated in the design of a Chinese autonomous vessel, and what vessel? GFA vessel, he asks.
Not really. My company Starry is not a part of GFA. Yeah. No, we are not a part of it yet.
Thank you. I think that you had some other questions following that. But...
Yes.
Thank you.
Yeah.
Good luck.
Yeah, thank you.
Dear participants, do you have any comments or any questions? You're welcome. So thank you, Mr. Lisin. And dear participants, some information, because our colleague from Brazil, he can't participate just now, as I was told. So there we are now 15 minutes past 11 in Russia and past 16 in China. We have provided for 15 minutes interval, pause, coffee break. So probably, I don't know your opinion, I just suggesting, probably we take now a coffee break for 15 minutes, and we resume our session not at 00 minutes, depending on the hour, but in 15 minutes. What do you think about that? Or we take probably a longer coffee break, as you like. Please, your opinions, and we'll decide as the majority would like to do. And so we take a coffee break for 15 minutes, and we resume our conference in 15 minutes. That is 16 in China and 11 in Russia. And I ask Mr. Zhilin Liu from Harbin Engineering to take his part of mediation of the next part of the conference. And thank you, dear participants and dear attendees. Thank you.
好的，休息15分钟。
Am I audible?
Yeah, it's okay.
Permission to share my screen. All right. All right. Greetings, everyone. Greetings, honorable lecturers, researchers, professionals, and fellow students. I'm sure that we are currently in various different time zones. So good morning, good afternoon, and good evening, wherever you are. And it is an honor for me, Maria Valencia, and I am representing my team, Barunastra ITS Robobo team, from Institut Teknologi 10 November in Indonesia, to share our research regarding marine autonomous technology with you. All right. First, I would like to introduce my team. We are Barunastra ITS. We are a research team focuses on conducting research on autonomous surface vehicles since 2012. We established by the university in Indonesia called ITS, by the ITS Robotics Student, Mathematics Club, and Hydromodeling Club. And we are committed to help foster the world maritime technology advancement, especially in Indonesia. So as a team, our vision is to develop autonomous surface vehicle to foster world maritime technology advancement, especially since our university, ITS, is one of the largest maritime research technology center in Indonesia. All right. Here you actually could see our boat lineage. So this boat lineage consists of more than 20 boats, which we have done in this past almost 10 years, from 2012 until the recent NALA Theseus for the 2022 International Robot Competition in Florida. Well, a brief story from us. We started from the 2012 with the national competition and the national unmanned vessel competition. And we actually started in the electric remote control category. And moving on, we start our international debut, and this is some moments of our competition in these past years. And we are moving on to our recent project, the NALA thesis, which we want to present in this forum. And so we are pleased to introduce NALA thesis. NALA thesis, it's actually our recent project, which we developed for the International RoboBoat Competition 2022 back in June 2022 and held in Florida, United States of America. And actually from this prototype, we have won the autonomy challenge and design documentation for the 4th time in a row, competing with 14 others country. And we also compete with other 240 students worldwide. So actually, the Theseus itself was a mythical king and a founder hero for Athens. And this mythology that we adopt from him is his role in history, which called a major cultural transition, like the making of the new Olympia by Hercules. The ship of Theseus' philosophy itself brought the experiment whether an object that has been that components has been replaced remains fundamentally the same object. Well, this is our prototype. The prototype dimension is 0.88 meters of length of all. It has a draft of 0.14. The overall height of the prototype is 0.78 and the height of hull itself is 0.21 meters and its beam is 0.69 meters. Then, as I said before, we have actually had more than 20 prototypes in our 10 years of research. This is the Theseus. The upper one is the Theseus. The lower picture is G4. In this comparison, you can see that with the same speed, the Theseus has smaller resistance and smaller volume fraction. And the simulation of resistance is analyzed using ANSYS Fluent and response amplitude operator using Maxsurf motions. And for each simulation, each model is simulated in the speed of 2 knots or 1.033 meter per second. Then for the competition itself, we bring the novelty of this design is called ship modularity. The modularity concept makes us able to travel from Indonesia to the US and also to do lots of design iteration and trial and error during our research. By using the modularity concept, we made a holo to connect 2 hulls since it is a catamaran hull boat, and it also becomes the deck of the ASV component arrangement. And mostly the components are above the waterline, which make the center of gravity slightly above the water. And to overcome this, low freeboard is the best option that we made. So the roll and pitch rotation can be kept to a minimum. So this is the rod that I'm talking about. This is the frame which connect 2 hulls for the ship. And we have watertight system. It is a box of what contains our electrical components so that it won't be affected by the water. We have an LED indicator, which is actually mandatory for the competition, but also be the sign of what type of operation that the ship's actually doing. We can have it on autonomous, we can have it on the remote, and if it is shut down. Then this prototype also have 3 thrusters with 2 azimuth thrusters mounted on the stern of the ASV and 1 fixed bow thrusters mounted on the bow area as shown in this figure. This is the fixed thruster. And the ASV would be able to perform 3 types of motion: pivoting, orientation lock motion, and path following. Pivoting is when ASV change its direction without changing its position. Orientation lock motion is when the ASV change its position without changing its orientation. And path following is when the ASV follows waypoint. Since it is a competition, there are some challenges that we have to do, and one of which needs a ball launcher, and this is the ball reload system. And one system as the ball launcher, we have also water blaster. And this is the ship software architecture. The software architecture of Nala Theseus uses the Robot Operating System, or ROS. And using the ROS, ASV software are designed to be loosely coupled ROS packages, where each package conforms to the single responsibility principle. This allows the ASV to easily use custom ROS packages from the previous RoboBot competitions, since we are competing for like 6 times, and have the development and testing of the ROS packages done individually. With this, the software development time can be shortened. The ROS packages deployed in Nala Theseus can be seen in this figure. The camera, RS LiDAR, MAVROS are responsible for obtaining sensor reading from the camera, LiDAR, P-Hawk inertial sensors, respectively. And the ASV perception package would subscribe to the sensor stream data, fuse them, and publish the information about the ASV and its surrounding and object information. For the ship version, we think that it is best to be explained with a video, and so this is the further explanation of the ship version.
From the ASV. Due to this, after trying several models, now Theseus uses one of the YOLO V4 architecture variants, YOLO V4 Tiny 3L, for its object detection model. This model was chosen for its speed and accuracy for small object detection. As this model is relatively small, it can be run at 15 FPS and on our onboard computer Jetson TX2.
Okay, so actually this would like to explain that we use 3 different model of ship version: the YOLO V4, YOLO V4 Tiny, and YOLO V4 Tiny 3L. The difference is that we use the YOLO V4 Tiny 3L because it is more responsive than the previous model. Then after our research, what is the outcome of our prototype? Here is our prototype at the International Robot Competition in June 2022 in the arena. There are various challenges in this competition. There are the Pathfinder, and then the docking challenge, and then the ski ball challenge. This is actually the ski ball to avoid the buoy that is placed in the lake. And we're moving on to the docking challenge. So this boat actually can pivot through the right docks without changing its direction. Right. Okay. Then the prototype has to go through several buoys and locate its object positioning. And this is the water blaster challenge. We have to fill an empty packaging inside that target. And afterwards, we move to the ball launcher challenge. So we have the reload system, like up here, the white one, and then it has to launch the ball to the target. And you can see here the LED is lighting blue in this camera, blue. It shows that this ship is in its autonomous mode. All right. So that's actually all from us. We hope to continue our research in the maritime autonomous technology forward, and please keep in touch with us and these links below. Thank you for your attention.
Thank you, Maria. Do you have some question? Do somebody have question? I ask a question. You said you have attended the IRC 2022 in Florida. So how many countries and teams participate in the competition?
All right. Thank you for your question. Actually, there is 14 countries, but there are several countries that send more than one team in the competition.
Do you remember if there are Chinese team?
Well, actually, I don't think so, because you can actually see the competitors in our Israel. We have from the Europe. We have a lot of team from the US because it is held in US, but I don't think there is any Chinese university team yet. Maybe we could compete in the next competition.
Another question, can you introduce what control algorithm used in your USV? Sorry?
I'm sorry, I cannot catch your question.
Can you introduce briefly what control algorithm used in this vehicle?
All right. Thank you for your question. Actually, I'm here with my programmer and my designer. Wait.
Oh, it's not, the control algorithm is not your work, okay?
Yeah. So we are a team of like 20 students, and we do it all together because we have different majors in the team, and we have Dion here as our programmer, and I'm sure that he will answer your question better than me.
Okay, thank you, thank you.
Okay, so for the answer to the question is that we used a PID-based algorithm to control the ship motion. So for example, to follow the path based on waypoints, we have our own modified algorithm such that the ship will always keep track on the path created by the waypoints instead of just merely following the waypoints. Now, with our algorithm, the ship can follow the path created by waypoints more tightly than just merely following the waypoint. And maybe for other types of motion, such as the orientation lock motion, it's actually function a little bit like dynamic positioning. We control our three thrusters, the two thrusters, azimuth thruster in the back and one single bow thruster in the front, with also the same PID-based algorithm. But we have a mathematical formula, linear equation to reverse compute how the angle of our azimuth thrusters and how strong our bow thruster should be, and that can be controlled by the PID controller.
Thank you very much. Do anyone have other questions? Other questions? Okay. Thank you, Maria.
Thank you.
The next report is from Admiral Ushakov State Marine University. Maria, can you stop your share? Okay.
Okay.
The next report. The next reporter is Victor Skakatko. He's a professor leading the research laboratory on automation of navigation and a group of researchers at the Admiral Ushakov Marine State University. The type of the report is the research laboratory on automation of navigation. Professor Victor?
Yes, it's me. Thank you, Chair.
Thank you. It's
Do
your
you hear
time.
me? Okay. Thank you very much. I represent the Ushakov Marine University, the laboratory of scientific research, automation of navigation. Our institute, universe, located on Black Sea coast, and at the moment we have accumulated extensive experience in the development of technological and technical solutions in the fields of autonomic navigation, especially in the field of autonomous port fleet. In the screen, you can see Novorossiysk Bay with many port vessels. My colleague, leading researchers Dmitry Studenikin, will tell you about this more details. I give him the floor.
Thank you, Victor. Please allow me to share my screen.
Just a second.
Can you switch the demonstration off? Okay, I'll try to do it. Is this one visible? Can you see my presentation?
Yes.
Yes, it is true.
Thank you. Let's go then. We represent our concept on the development of fully automated tugboats. And let's get started. Has the slide switched? I suppose it has. Okay, as for the mooring operations, we divide the process into the following section. Apart from escorting the ships, thus is turning the vessel to the required position, securing the vessel, and ensuring the safety of the vessel, as well as the departure of the vessel from the berth. Most of the tugboat used operations.
不差那几天儿，那有啥差别啊？不差那几天儿。
苏丽老师，静音。
只是咱们俩听。
静一下音啊。
Thank you. Most of the tugboat operations are interconnected with the dramatical drop of vessel speed, and that goes to the following consequences: radical complexation of the interaction with the vessel, loss of the vessel's ability to operate safely on its own. And if the tugs are used, the multi-agent management system should be applied. Well, let's get the problems on the table. First one is the concordance aspect. As you might know, there's a master pilot information exchange procedure that includes various checklists, various information exchange portions, and so on and so forth, that should be in the ship's management system. However, we've done some research on this one. The values of the Kendall coefficients of concordance in the respect of the tugboat versus shipmaster shows 0.8 or even as low as 0.7. However, if you want the system of tugboat and the vessel to be successful in the aspect of concordance, the value should be above 0.9. So, in simple words, the concordance aspect can be a problem. It might not be, but it can, actually. The next one. Of course, as all of you know, the tugs are using their taglines, and that comes with a whole bunch of problems. as a sea mariner, I've often seen that the tug line is torn, and as well, as it represents the immediate danger to the crew, it might represent if broken in inappropriate way. Sorry? Okay. Actually, if there's a congested space, the length of the tug line can be a problem. When using a tug line, you have a time delay between your command to the tugboat and actually the effect of the tugboat on the vessel. Taking our latest research into account with the risk-based system of tugboat lines, there are a lot of relevantly unevident specifications in this matter that can lead to serious risks as well as raising it to the point of 23 or 24%. What we propose is quite simple. We introduce our concept of the automated tugboat, and the attachment to the ship is magnetically based. Here you can see on the picture how exactly ship will be escorted and turned into position. First of all, the fully automated tugboat from our side is currently in research. However, we do have some technologies on hand or close at hand. We have developed advanced fuzzy logic awareness system that allows the advanced reading and interpretation of all data sensors that come from the automated tug. We have innovative movement solution suitable for tug escorted vessel group. That includes movement, control, and collision avoidance system. That also includes chaos theory based prediction system that allows us to predict in the best way available the movement of other vessels. And what we are doing now, the solution is close at hand. Actually, we have the math for it, but it's not, its content is yet under research. The quality of decision evaluation system. So we can measure the quality of the decisions made by any system. With this, there's one actually possible problem. The hulls for cargo vessels should be reinforced in the places where the magnetic tug attachment is to be implemented. It's actually a basis for discussion. I'll go to it a little bit later. There's our automatic tug concept. Actually, we had it in model, but I think this picture is most adequate for this conference. The automatic tug, as you can see, has mooring devices which are to be used in the places within designation of tug to perform its actions. And now the proposed place for discussion. As well as you know all, there's a classic electromagnetic berthing system that is widely used, and it is not actually required to have some reinforced places for the usage. However, the tug is not a berthing system. It might have different loads, it might have some movement aspects, and so on and so forth. So the discussion is to be held whether we need actually the reinforced hull for the use of this magnetic tug. Okay, and now comes our proposal for cooperation in the field of mass. We wish to work in these lines, but not limited to, of course. First, we want to join our efforts in the development of some maybe conception, maybe framework for the mass shield building for the implementation of autonomous navigation. Namely, the discussion if we need a reinforced plate. Then the joint development of cells of electromagnetic mooring devices. And we offer to share our experiences on the experiments of autonomous navigation involving pilotage and mooring in autonomous mode. And then, thank you for attention.
Thank you very much. Do anyone have questions? Questions? I have a question. Whether the electromagnetic mooring device will consume a lot of energy?
From our perspective, it will not. Because the most energy impact will be when the electromagnetic system attaches to the hull, and then we need energy only to sustain its state. Thank you.
Thank you.
I have a question. I have a question. My English is not well, so I need a translator. 那我的问题就是，你现在做的全自动拖轮的开发，那么你们已经有了实船了吗？做过实际的这个拖轮试验吗？
李波，你来翻译吗？
No problem. So this is the question from the Professor Xia Guihua. His question is that whether you have implemented some real testing or real experiment in the water, in the open water. Thank you.
Well, that depends on the system we are talking about, or we are referring about. If you're referring to the whole automated tug, that is scheduled for the future. But some systems such as navigation system and awareness system are already tested in the water and showed great results. Thank you.
Thank you.
Any questions? No question. So, thank you very much. Thank you very much.
Thank you.
Thank you.
Thank you.
Now we begin the next report. The next report, the title is maritime object recognition. The reporter is Luo Xiangfeng, researcher and associate dean of School of Computer Science, Shanghai University. He is the Shanghai Outstanding Academic Leader and the leader of Shanghai Key Innovation Team. So, Professor Luo, it's your time.
So, hi, I'm going to represent the work is present Professor Luo.
Okay.
So, okay.
Сейчас сделаю. That's okay.
So, thank you. So thank you having me here. And I'm Yansun. I'm from Shanghai University. And today I'm going to talk about maritime objects recognition. So first, I will introduce our research team. And here is the research group. And we have more than 10 researchers and more than 60 graduate students working on this. So, so I will give a talk in the following three aspects. So first one is multi-scale object detection. And second is small object detection. And the third is fine-grained object recognition. All of these problems are important to autonomous navigation technology. So first is multi-scale object detection. So for identify objects, feature extraction is the basic method. However, the ships on the sea surface have different scale, which bring challenges to identify those ships. So in order to extract rich multi-scale feature information and improve the accuracy of multi-scale object detection, we propose a method based on hierarchical feature attention strategy. So first, we design a contextual information extraction module. It uses different dilated convolution to extract contextual feature with same scale, but in different receptive field, which can enlarge the feature range on the image. Second, through the hierarchical feature fusion model, the feature information of different scales is fused to form the feature map with rich spatial and semantic information. The lower scale features offer spatial information and the higher scale feature offer semantic information. Finally, the visual attention mechanism is added to the fused hierarchical feature map. It extracts a more identifiable multi-scale shape feature. It can also remove redundant features, thereby improve the accuracy of different scale shapes detection. So here we show some experimental results that we apply our method on maritime object detection. So from the picture, we can see our method can detect ship in different scale precisely. Also, our method can be applied to detect a different scale aircraft, since those aircraft are also suffer from same problem. We can see from the result here, our method works very well. So here is a demo that we apply our method on detecting moving objects in traffic scene. So from the demo, we can see our method can detect a different scale precisely, even they move really fast in the scene. So the second part is small object detection. The ship on the sea surface usually have different scale. So some of them are extremely small, especially those in long distance. You can see in the picture A, there's some boats that is really far away. So, so first, the small ships, they have low resolution and only account for a few pixels in the image. So for small ships, those character makes them only have very limited effective information. So this is a disadvantage for our to detect because we can't extract valid information from those pictures. So that is the key reason for the poor detection result of small objects. So how to accurately detect small ships is very challenging. And second, the complex marine environment usually has severe interference to tiny ship detection, such as wind, wave, ocean current, and other complex conditions. As you can see here in the picture C, you can barely see the ships in this picture because of the weather. So under this complex background, the information of small ships will be weakened by the environmental noise, or the small ships just blended with the background, and the collected image, they lacking obvious contrast in the collected images. So this is also one of the factors that will cause the difficulty of small ships recognition. So finally, in the convolutional neural network also has drawback for small object feature extraction. Most state-of-art object detection model, they go through multi-convolutional downsampling operation in their backbones, such as VGG and ResNet. So for extracted deep semantic information and increase the perceptual field. However, most small objects, they only have very fuzzy edges and only little semantic information. After those multiple layer neural networks, it may lead to serious information loss. So the extract feature, they even cannot be passed into the object classification and the regression networks. So for detected tiny objects, people usually use feature enhancement approaches. This kind of model, they can improve the feature characters of small objects, but the current method, they do not differentiate and refine the feature according to different layers. So they directly use shallow features with higher level features. So this might lead to problems such as the feature redundancy in the fused features. So will increase the computation cost or lead the fail detection. So based on this consideration, we propose a new feature enhancement-based small object detection method for their weak features and fuzzy edges of those small ships. So first, we design a shallow spatial features. This a shallow spatial feature enhancement module. It extracts rich shallow spatial features through a lightweight hourglass network. And then we fuse the extracted feature information to the pre-trained backbone network to enhance this information. And second, we design a high-level semantic feature enhancement module. Through the densely connected feature pyramid network, the middle-level features are effectively transferred to the high-level features. This method can enhance the high-level semantic feature information. And finally, a super-resolution enhancement space is used to enhance the resolution of the high-level semantic feature maps. It can improve the localization performance of small objects. We apply separate classification and regression on the enhanced different scale feature layers to further improve the performance of small-scale shape detection. So this strategy not only effectively enhanced the shallow spatial feature information, but also the high-level semantic feature information, therefore improve the robustness of the small shape detection results. So we combine the multiple scale and the small object detection method together and apply it to the SmartShip project. In this project, we collected over 22,000 ship pictures, and 80% of the data is divided into a training set, and the rest 20% is set as test set. So detection accuracy of our method can achieve 95%. Here is some experimental images that we apply our algorithm on the ship data set. So from those results, you can see we can detect the tiny ships precisely, and also the different scale ships. Here is some dynamic detection result here. And also we can use it detect aerial objects as well. So here is multiple aerial objects. So the last part is fine-grained object recognition. So as shown in Figure 8, the two ships are container ships and the bulk carriers, which are very similar in shape and the color. And the main visual difference is whether these two ships carry containers and other cargoes or not. So different subclasses of the ships often only have small visual difference, which makes it difficult to classify. Secondly, the intra-class of fine-grained ships usually have large difference. They make the recognition of ships that belongs to same subclass easily deviated, as shown in Figure B and C. In Figure B, both of these ships are bulk carrier, but the color, shape, and the scale of them are all different, which will cause failed identification. And in addition, the two ships in Figure C, they are both passenger ships, but they are captured in different angle, so they have significant difference. This will make a big impact on the recognition result as well. So generally, fine-grained ships have smaller interclass difference and large intra-class differences. Also, it is difficult to find discriminable information that fully describe the ship's details in different subcategories. So last and not least, in the actual marine scene, the classification is also affected by the weather and the background. So this will bring more difficulties and challenges to the recognition. So in order to achieve accurate and efficient recognition results, we also propose a method based on multi-scale feature refinements. This model contains 3 parts. So the first is Coarse Grained Object Localization Model. This model used the region proposal network to locate object candidate region on the hierarchical feature map. It can find discriminative object regions in the image and eliminate redundant regions to reduce the search area. Meanwhile, it's able to roughly adjust the location and size of the object to provide better initialization for subsequent fine-grained recognition. Second, in order to learn the fine feature, a multi-scale feature refinement module is designed. The module converts the original predicted feature layer into a hierarchical feature map, which contains rich contextual information for achieve more accurate objects, fine-grained classification and localization. The information refinement of the multi-scale feature map is implemented by cross-layer fusion of the bidirectional feature pyramid structure. And finally, the fine-grained recognition model is used to perform accurate position regression of the localization corresponding region on the refined multi-scale feature map. We're predicting different subcategory labels to achieve accurate fine-grained shape recognition. So here is some results we applied this model on the data set. In the left is some data that we collected from real scene. So here we can classify those shapes accurately. And on the right side, there are some images that we collected from internet. Those pictures are easy to recognize, and our algorithm performs on those data. We can achieve 85% accuracy. So that's all. Thank you. Thank you for attention.
Thank you. Thank you, Sun Yan. Do anyone have questions? Any questions?
Oh, yes, I have a question. Thank you for your wonderful presentation. You mentioned the result of your research has applied to a project. Would you please tell me more information about the project and furthermore, and do you have the whole system for recognition or equipment system you have got independently or cooperated with other companies? Thank you.
Oh, okay. So this is a SmartSheet project, which funded by the country, and so our research group is in charge of the visual part, and we take pictures from the real scene, and we use those data. We design models and to predict it, those real data we collected. And sorry, can you repeat the next question?
Oh, yes. I mean, maybe for your research results, models and algorithms and something like that. I wonder whether you have the equipment for using your achievements.
Oh, yes, we have established the whole system to detect the objects, but the system, the software system and the hardware is separated. We collected the data, and we used the software system to detect those ships, and we have so it is also easy to so embed those the software on the hardwares.
Oh, thank you. Maybe I would like to contact with you in detail after the meeting. Okay, thank you.
Okay, thank you.
Okay, please.
Thank you. Any questions? Thank you, Miss Yang Sun, for interesting details. Tell me, maybe I missed it. What do you think should be the sample size for training a neural network with an accuracy of 97%, like a human, 97%? How much photo? Thank you.
So actually we have 22,000 images, and we use 80% of the images as training sets, and the 20% as the test data. And for the object detection, so for the small ships and the multi-scale ships, the detection accuracy is, our accuracy is 95%. But for the classified ships, like tell what kind of ship this ship is, we have 85% accuracy.
Thank you. Thank you.
Okay, thank you for your question.
Are there any questions? Other questions? Okay, thank you, Sun Yan. Thank you very much.
Thank you. Thank you for having me.
The next report, the title is the vice. Let me see. Vice Rector for Digitalization, Innovation, and Priority Projects. The reporter is Alexei Titov. He is a Vice Rector for Digitalization, Innovation, and Priority Projects of Astrakhan State University. He previously worked as the head of the Engineering Project Office of Astrakhan State University, then took over as Vice Rector for Innovations and Priority Projects. So it's your time.
Dear colleagues, unfortunately, Alexei Titov will not be able to join us, but his presentation will be available together with everyone.
Okay.
Absolutely.
So Alexei Titov can't be here. Have anyone else to give the report institute?
Next. Next participant, please. Heo Feng.
I see. So the next report. The total of the report is cancelled. Okay.
Okay. Next.
Okay.
Next class.
Okay. So the next report is Feng Hui. He's from Wuhan University of Technology. His report is visual perception technology for ship intelligent navigation. Professor Feng.
Hello, could you hear me?
Hello. Yes, it's your time.
Okay. Please see the screen.
Yes.
Okay. Thank you.
Okay, you can begin.
Okay. Ladies and gentlemen, my name is Feng Hui. Welcome from Wuhan University of Technology. Today, I want to share our recent research related to visual perception technology in ship intelligent navigation. My topic has 3 parts. We know that 21st century sure starts the intelligent age. Plenty of smart vehicles and devices have been appeared in our daily life. Some robots, driverless car, smart ship, and driverless truck began to use on the road and at top, and make society safer and more efficient. The Chinese government make great effort to prepare the development of smart ship in recent years. CCS, MO, Lois, and DNV has successfully launched the code for smart ships. The intelligent navigation plays a very important role in reflecting the smart level of ship. So we focused on this technology in this topic. If we want to realize a first-to-birth intelligent navigation, main step include first, we should use perception technology to perceive the state and the environment information. The environment information includes the state of ownership, ownership and the other ships sailing on the water, and then providing the route decision making suggestions. The decision made require the navigation regulations. Finally, control the ship along the optimal route. So if we make concluding, the intelligent navigation include 4 technologies. They are intelligent perception, intelligent design, path planning, and intelligent control. Under each technology, there are several problems to be solved. For example, the task of intelligent perception including object detection and recognition, multi-sensor fusion, and so on. Intelligent perception is our research interest. This table lists the sensors used in the perception. Camera has a lot of good features, such as its low cost and rich in details and semantic information, which is designed to replace the human's eyes. We know that the driverless car are developing much faster than smart ships. In the application of driverless car, there are 2 main roadmaps for intelligent perception. First, Tesla uses pure visual perception solution without any other sensors. Most of the rest company use multi-sensor fusion solution, including camera, lidar, radar, and so on. Neither of the 2 solutions is perfect now. Traffic accidents often happen on driverless cars, but it is not that vision perception is one of the most important perception methods. Okay, let's focus on visual perception technology. Visual perception is that use the cameras mounted on a smart ship to detect objects on water, such as ships, a bridge, and other obstacles. Early research used traditional methods such as pattern recognition, machine learning, and so on. With the development of deep learning, especially convolutional neural network or CNN, use supervised learning to train a deep neural network model can better detect and recognize objects. The typical object detection method based on CNN include 2-stage method and 1-stage method. This is a structure of 1-stage method, ULV5. Although the network structure may seem complex, we can divide into 3 main parts based on its function. The backbone is used to extract features, and the detection head is usually used as a classifier and regressor to predict bundle box and class. The rest part is usually called detection net, which is designed for views high-level features. Okay, here are some surface images. We are more likely to detect objects from these images. However, surface object detection faces many challenges. For example, sea fog reduces the visibility of the target, and the shape of shaking of the hull causes the deformation of the target. and different illumination makes the target recognition difficult. And the movement of the hole will also cause motion blur. The consequence is that the accuracy of object detection will decrease. The false detection and missing detection of small targets is frequently happened. This consequence will bring safety risk to the navigation of ships. So, improve the accuracy of surface object detection is very important to improve the safety of ship navigation. Okay, let's first look at the blurred image. The two major reasons cause this phenomenon. First, the ship's attitude change frequently due to the influence of wind, wave, and current. And second, the relative motion between the camera and the target. So sometimes in the blurred image, you can see this column. The target contour and texture are unclear, and the color is also distorted. If the image is not enhanced, it will be difficult to avoid false detection and missed detection. So we try to blur the image and recover the clear image before we detect the object. To tackle this problem, we propose a motion blurring method, SharpGAN, based on generative adversary network or GAN. To our best knowledge, this is the first work we use GAN to recover the blurred image. The network consists of two components. Generator restore the clean image from blurred image. Discriminator used to identify the restored image and the clear image and guide the generator. The generator and discriminator can regard the two sets of a game. Until they reach an imbalance, the training process of the entire model is complete. In this network, we also use RB bandlight to strengthen the ability of feature extraction. We also propose a feature loss, which is used to extract a different level of features to guide the generator to learn more effectively. These are experimental results. At first, we compare restored image by using different deblurring methods. The last line is our method. Some region has zoomed in. From the results, we can see that the proposed method is able to recover more detail of a blurred image. On the right side, we use the restored image to detect targets. It's easy to see that the proposed method is better than others, especially small objects. We can look here. And for the same object, the detection probability is higher. The quantitative results also support the above conclusions. Consider that if we want to detect the object from blurred image, the traditional method may use two steps. The first step is image deblurring, and the second is detection. If we use the method proposed before, we need to train two separate models. One is to enhance the image, and the other is to detect target. It looks weird. So we proposed an integrated deblurring and detection network based on GAN. We called it added GAN, trying to solve this problem in a single network. The network is composed of three parts: the generator, discriminator, and the detector. If we compare this network with the above-mentioned SharpGAN, a very interesting change in structure is that the discriminator and the detector share the same backbone. Thereby, the complexity of the network reduced. Additionally, in the training stage, the detection loss as well as adversary loss will feed back to the generator help to generate better enhanced image and eventually improve the detection accuracy. So with this network, we can input the blurred image and output detection result in a single network. We have compared the performance of IDD-GAN with SharpGAN and other two state-of-the-art methods. From the results, we can see that the proposed method is better than others, and some small bolts can be detected, even the input image are blurred. Okay. We know that there can be some kinds of distortions in actual water surface images, such as hazing, blue and long lights. Even with the previous integrated network, multiple networks are still need to handle different tasks. This problem motivates us to research a multitask network. So we propose integrated multitask debluing, hazing, and detecting network. We call it DCubeNet. The purpose is to accurately detect and recognition targets, regardless of the input is a blurred image or a hazy image. This network also contains three parts. The shared layer of backbone has two branches. The first branch is used to extract shared features, and another branch is used as a classifier to distinguish between blurred and hazy image. In the conditional layer of backbone, feature extraction is carried out according to the different image with blue or haze. The last part is detector. By using this network, no matter the input is a blurred image or a hazy image, it will be enhanced and output detection results. So the entire network looks compact and no enhanced image is generated during the procedure. We compare the detection result in blurred and the hazy image by using different methods. This line is our results. We can see that it is better than the state-of-the-art, both in terms of accuracy and the efficiency. And these results are in rear image. On the left side, we test on the blurred image. On the right side are on hazy image. Last line is our results. We can see that the targets are better detected and have few missing detections. So to sum up, in this talk, I introduced our research work related to visual perception from image debluing to integrated debluing and detection. And finally, we propose an integrated multitask network to adapt to different application scenarios. It's not to say that this framework is not limited to the blue, the haze. It is an extendable framework, and it can also used in low light images and other similar tasks. At last, based on the algorithm we have studied, we can conduct the test on a container ship from birth to birth. I speed up the video playing. The ship is leaving the port. We can see the majority of objects have detected and recognized noise sealing on the ocean. We can see that fogs on the sea is noticeable. And at the end, the ship is arriving at Newport and stop at berth. Okay. That's all for my share. Thank you for listening.
Thank you very much. Thank you, Professor Feng. Do anyone have questions? Anyone questions? Your work is
I have a question.
okay. Please.
Hello, Professor Feng.
Hello.
Good afternoon. Question about that. In your application, use your system for container ship. First problem. How many cameras are used in practice in your application?
Do you see how many cameras used in our application?
Yeah.
We just use one camera.
Only one.
The main, yes, it is a main camera mounted on the ship.
Only one. Okay. Next question about after you detect the object, you will classify the shape, the object. Okay. How many kinds of shapes distinct you classified?
How many images used in the data set?
How many kind of shapes you had classified?
Yes. We collect many kinds of images from our cameras because we have constructed several boards to collect our images, and we also collect the image from network. So these images are from different perspective. So we use this image to train our network. So it is not just from one camera data to train the model.
Okay. Thank you.
Thank you.
I have a question. The video, very outstanding work. The video you show me is just a experiment or a commercial application.
No, it's just a test video which is used to verify our algorithm we have proposed.
How's that? Very good. Anyone? Any questions?
Thank you. Thank you for report. Big interest. Are you planning to combine conventional and infrared cameras on the ship? Yes, no? Thank you.
Sorry, I didn't catch you.
Combined conventional video cameras and infrared cameras on the ship. Combine
with other sensors on the ship. No, we just use a camera. No. We just use a visible camera.
Yes, in full dark infrared cameras, full darks.
Thank you.
No questions? Okay. Thank you, Professor Feng.
Okay, thank you
very much. Next report. Advanced training programs and simulators for math specialists. The speaker is Rodolphe Sergi. Yes, Rodolphe Sergi is the Deputy Director of the Academy of Water Transport of Russian University of Transport. He has long been engaged in the safety of navigation in the Ministry of Transport of the Russian Federation. So, Rudolf, it's your time.
So, thank you. Good afternoon, ladies and gentlemen. So, the topic of my report is Advanced Training Program and Simulators for Math Specialists. And let's start. Currently, maritime navigation is entering a new stage of scientific and technology development. The practice of managing sea vessel by shipping company is changing. If earlier such control was limited to the limited exchange of documents and filling the certain reports from ship and radio correspondence, now companies are moving to remove control of their vessels. Describing the main causes of accident at sea, the International Maritime Organization identifies two main reasons: technical, which account for 20% of accidents, and the so-called human factor, which account for about 80% of navigation accidents. The objective prerequisites for the accident rate of the fleet are the growing speed of ship, increasing the ship size, and also increasing the ship traffic. The subjective side of connected with the managing link, the navigator human. The navigator's decision-making, the influence by his physiological and neuropsychiatric state. Fating the harmful working condition at sea lead to a decrease in the efficiency of the navigator. Therefore, an urgent scientific problem is to reduce the influence of the human factor in the development of decision on ship management. During last years, Russia has significantly increased interest to ensuring the safety of navigation using modern information technologies. In general, it should be noted that the management of vessel for the purpose of their effective and safe interaction is a complex problem. One of the hand methods and algorithms are required to control the interrelated action of individual vessel and at achieving common goals. On the other hand, it is necessary to develop methods and means of implementing this action to real time and taking into account the change taking place in the environment. The solution of this problem is possibly only with comprehensive study of navigation safety issues and the construction of an automatic hardware decision support system capable of solving navigation safety problem in the shortest possible time with maximum efficiency. The function of maritime autonomous surface vessel is carried out in real time, which requires its integration with the means of motion control and navigation condition available on the vessel when operating the mast. It supposes the solution of the following tasks: identification of vessel located in the zone of possible collision, monitoring of vessel, movement parameter and dynamics of their change, estimate of the error of the obtained motion parameters, classification of vessel according to the degree of danger, determination of the set of interactive vessel for which scenarios of possible movements are formed, determination of the area of mutual duties of vessel, their complex with the correct, and the boundary of the safety zone of their own vessel. Formation of the variety of possible strategies for the movement of ship, determination of traffic strategies that mean the special safety criteria. A holistic view of the safety of masts should focus on the need to identify all management mechanisms. Therefore, the main task of the mast is to ensure comprehensive safety at sea. The constituent aspects of which are navigation safety, ship collision prevention, internal and external integrity of the vessel. In 2023, it is planned to start operate autonomous ferry in the Russian Federation. In order to train crew of autonomous vessel and operators of the Center for Remote Control of Autonomous Vessel, the Russian University of Transport has developed an advanced training program for captain and navigators of autonomous vessel. Captain or chief mate of marine vessel with experience working on autonomous sea vessel for 12 months over the past 5 years will be admitted to the training, or with experience working on the marine vessel without requirement for autonomy for at least 3 years. During the training, students will acquire the following professional competence: the knowledge of relevant international maritime convention and recommendations, as well as national legislation in the field of math, artificial intelligence, machine learning, human-machine interaction, identification of the status of an autonomous vessel, monitoring and control of the status and movement of an autonomous vessel, interaction with the ship traffic control system, action in case of accident, implementation of measures to prepare for the response to cyber incident, assessment of vulnerability to cyber attack, and effective response to cyber security and cyber safety incidents, implementation and control of the cybersecurity plan to minimize cyber risk. In order to provide practical training for navigation operating autonomous vessel, the Russian University of Transport has developed a navigation simulator for autonomous navigation. The simulator will allow for practical training of navigator of 3 levels of autonomous vessel defined by International Maritime Organization. The first, the autonomous vessel is controlled by the crew. A navigation system are used to support decision making. The second, the autonomous vessel is controlled remotely, but the crew is on board. And the last, the autonomous vessel is controlled remotely with no crew on board. And our university plan to start training captains and navigators for autonomous vessel in 2023. Thank you.
Okay, it's off. Professor Khodov is finished?
Yes, yes. Thank you, I'm finished.
Very good. Thank you, thank you. Any questions? Do anybody have questions? I asked the question. You have a virtual trainer simulator to train the student. And can you introduce the this autonomous navigation simulator in detail?
Now the simulator, our simulator is not ready yet. We plan to finish the development the next 2 or 3 months, and it not the navigation simulator. It will be a simulator for autonomous vessel.
So it's just it's a very virtual software or a semi-physical machine. If the human is in the closed loop, and just virtual software to train the student. It's a completely virtual or semi-physical or human in the closed loop. Sorry.
Maybe he's not online now.
It's not online. Okay, the time is limited, so we continue. The next report is formulation control of unmanned surface vehicles under complex communication conditions. The reporter is Xia Guihua. He is a chairman of ICNAME, professor of Harbin Engineering University. He has been engaged in the research on control technology of naval architecture and ocean engineering. So, Professor Xia.
那这个报告还是由那个江祥利来完成，带我来做。
This report is be given by Jiang Xiangli Institute.
Okay. Let me enjoy my slides. Okay. Hello everyone. I'm Dr. Jiang Xiangli. It's my pleasure on behalf of Professor Xia Guihua with Harbin Engineering University to report my group's research on formation control of unmanned surface vehicles under complex communication conditions. The presentation comprises 5 parts, including research significance and synopsis, stating research purpose, performing research contents, conclusions, and outlooks. In the first part, we state the significance on formation control with complex communication conditions. As a class of intelligent marine platforms, unmanned surface vehicles have recently stirred up increasing research interest in a variety of theoretical and engineering communities. Then, facilitated with local communications, network surface vehicles can be cooperatively controlled to accomplish certain missions with rapidity, reliability, and low energy consumption, such as source exploration, environment monitoring, and multitask allocation. In general, all surface vehicles are collected to move under an expected pattern. This gives the rise to the scientific research on formation control of unmanned surface vehicles. Actually, the real-life ocean environment is full of electromagnetic interference and wind wave current disturbance. This may induce the network vehicles to be under complex communication conditions. However, such conditions may degrade the system performance or even destabilize the formation system. In this report, topology switching and the communication delay are employed to model the complex communication conditions. Note also, the information is usually transmitted via physical channels. They are encountered with communication interference, traffic congestions, and disturbances. On this basis, the second part gives a brief review of the most recent scientific works on formation control of unmanned surface vehicles. There are 2 issues on the formation control, that is the formation strategy and the network communication. A great mind encouraging formation strategies have been proposed, including behavior-based, virtual structure, and leader-follower. From the table, the strengths of the behavior-based formation method is easy description on individual behavior, but the weaknesses are difficulty in stability analysis, inability in global movement characterization, and non-scalability. For the virtual structure formation method, its strengths are easy characterization on the global movement and high accuracy, while the weaknesses are less flexibility and non-scalability. Additionally, the strengths of the leader-follower formation method are simple control design and conversion to trace tracking, but the weakness is fragility to the leader. To integrate strengths while overcome weaknesses of the mentioned formation strategies, this report promisingly proposes the leaderless consensus-based formation method. Although characterizing the global movement may be difficult, it preserves simple control design based on the leaderless consensus, high flexibility, scalability, and robustness to the leader. For the network communication, most literature commonly assumes the data transmission is continuous and the network communication is given by a fixed topology without any transmission delay. This may be unrealistic and run counter to the undesirable effects of the complex communication conditions. Then, in the third part, we state the purpose of the research on formation control under complex communication conditions. This report concerns the formation control design of multiple surface vehicles under complex communication conditions, modeled by topology switching and transmission delay. By introducing the transformation into the kinetic, a novel modeling of the vehicle is regarded as a matched system. This may simplify and analysis and synthesis. Considering the hydrodynamic parameter uncertainties, the non-fragile technique is employed to recast the process control with uncertain parameters into the problem of non-fragile control design with process parameters. In addition to the continuous data transmission strategy, the sample data technique is also employed in the formation control design so that the formation pattern is achieved with reducing the number of information updates and saving communication resources. Based on the purpose, the first part presents the main results on designing the formation under complex communication conditions. We consider the vehicle model in the borrowed handbook. The physical meanings of the vectors and matrices are standard. For this purpose, we assume it is norm-bounded, that is, its norm is bounded by a positive constant. In this figure, it's apparent the desired formation is achieved if the two triangles are congruent. Then, based on the definition 1, and by giving the relative formation configuration, the achievement of the desired formation is recast into designing control laws, so that there holds one of two equivalent conditions. Defining a new vector, we transform the vehicle model as the following system. Then calculating the relative formation error and making simple integration on the vehicle model, we easily derive the integrated formation error system. Note that the matrix B is full of column rank and the matrix pair A and B is stabilizable. Then, based on the derived integrated system, we promisingly recast the formation problem into leaderless consistent control of the integrated formation arrow system. Then the research in this report includes 3 contents. That is continuous formation control respectively under random topology switching and transmission delay and the sample data formation control design. Firstly, we concern the continuous formation control design with random switching topologies. In this content, the topology is considered to switch in a graph set. The evolution is governed by a continuous Markov signal. Then we design a control law containing switching topology characteristic. This can derive the formation arrow system as a closed loop dynamic. Based on non-singular transformation and stochastic stability analysis, the concerned formation problem is tackled and the precise expression of the formation reference function is determined. Referring to our research works can get more details. In the simulation, we collect 4 vehicles to form a triangle pattern in Figure 1. The 4 vehicles are interacted under topologies in Figure 2. In Figure 3, the evolution of the switching signal is plotted. As is shown in Figure 4, the desired triangle formation pattern is eventually achieved. This completes the flow. The second content concerns the continuous formation with transmission delay. The information interaction among neighbor vehicles is with transmission delay described by a time varying function with low and upper bounds. The control law is designed by containing a time varying transmission delay so that we derive the closed loop formation arrow system based on non-singular transformation and the Lyapunov-Kravtsovsky stability analysis. The problem of continuous formation control with transmission delay is tackled. Also, the precise expression of the formation reference function is also determined. More details can be found in our research works. To perform the simulation, 4 vehicles are collected to form a diamond pattern in Figure 5. The fixed topology in Figure 6 abstracts the network interactions. It has been shown in Figure 7. The 4 vehicles eventually achieve the diamond formation pattern. In the third content, we concern the problem of data sample formation control. This content performs the formation control design within the framework of data sample with a periodic intervals. Denote the sample instant to derive the sample interval. Assume all sample intervals are bounded by a maximum allowable interval. Then we collect sample information to design a control law. On this basis, we derive the closed loop formation arrow system. Introducing an artificial time delay, we conduct non-singular transformation and Lyapunov-Kravtsovsky stability analysis to tackle the concerned formation problem. To get more details, one can refer to our research works. The simulation collects 4 vehicles to form an up arrow in Figure 8. The interaction is abstracted by the fixed topology in Figure 9, as is shown in Figure 10. The up arrow formation pattern is eventually formed. Then the fifth part makes conclusions and give future directions. Firstly, we make some comparisons on the mentioned research contents. It follows from the table the sample data formation control has not concerned the complex communication conditions. Then the future theoretical research is to consider neighboring information is a periodic, sampled and broadcast over physical channels with random switching topologies and mode-dependent time delays. However, the key problem is how to determine the interplay among maximum allowable sample interval, transformation, delay information, topology switching characteristics, and network structure. Moreover, for the network optimization problem, the research direction is how to determine the maximum allowable sample interval for getting the maximum convergent rate with smallest possible data transmission rate. Then, by considering some uncertainties such as disorder, data congestion, and packet loss, the essential problem is how to model and smooth the mentioned uncertainties for regulating information. Because the validations in this report are merely performed in numerical simulations, our field work will conduct prototype experiments on Dolphin 1 and Intel Marine research and test unmanned surface vehicles moored at Qingdao Port. Another research work will focus on building a semi-physical experiment training platform for swarm exercising and maneuvering. The initial idea is to include 3 modules, including physical sensing and control module, information collection and processing module, and situation awareness and remote control module. This is all my presentation. Thank you.
Okay, thank you, Jiang Xiangli. Do anybody have questions? Any questions? Okay, Chairman, I ask a question. The Brazil and the report from Brazil is cancelled. It's okay?
Thank you all. Thank you, everyone.
Chairman, I ask a question. The Astrahan State University and the Brazil, the report from the Astrahan University and from Brazil, both of the former report is cancelled. Okay.
Yeah, unfortunately, there are several participants are not able to be here with us. We are very sorry for that. But as for today, I think that all who can participate already delivered their reports.
Okay. So the time is limited. So let's welcome the chairman from Russia University of Transport give us a closed speech, and then the chairman from Harbin Engineering University, Xia Guihua, gave us a closed speech separate, respectively. Russian first, okay, please.
Hello, every
校长，我让俄罗斯也先说几句，然后你再讲。
好的。
可以。
Thank you, Mr. Moderator. We are very glad that this laboratory had a chance to meet again, and we are very pleased to see all of our participants here. We hope this is one more step forward within the mutual developments we are doing right now. We also believe this our meeting will be is a step ahead, and we hope that we have a bright future, and we have some projects to discuss next time, and some developments to be considered together. And for us, it's a good event, very nice meeting, and tremendous platform to exchange our views. And we appreciate greatly all who found the time to come and to deliver their reports and presentations. Thank you all for participating in this event.
Thank you very much. Professor Xia, please.
首先啊，非常感谢今天这个来自于这个俄罗斯、马来西亚和中国的各位专家做的精彩的报告，这是我们对这个3个国家在自主传播航行技术研究方面又有了深入的了解。
Thank you a lot for all the friends and the professors from the Russia, Malaysia, and China delivering the reports.
李波，我是印度尼西亚啊，你纠正一下。
Sorry. Thank you a lot for all the participants from the Russia, Indonesia, China, delivering very good reports on the autonomous ship and related technologies.
那么通过这次会议呢，应该增进了我们这3个国家相关大学的了解，这个也呢为未来的合作奠定了基础。
And through this event, the relationship between the universities, among the universities from the 3 countries has fastened, and this also laid the foundation for the future cooperations.
那么我希望会后我们把今天大家做的报告的 PPT 统一呢收集起来，发给参会的各位专家。
I propose to share all the slides of the speech to share it among all the participants of this event.
那么最后呢，再次感谢我们俄罗斯交通大学、武汉理工大学、哈尔滨工程大学为办好这次会做出很多贡献的各位老师同志们。
And at last, thanks again to the university, Russia University of Transport, Harbin Engineering University, Wuhan University of Technology for the contribution to this event. And thanks to all the people who delivered very good speech.
那最后呢，我代表 ICNAME 祝大家新年快乐，万事如意。
And finally, on behalf of ICNAME, I wish everybody a very happy new year, and everything goes well.
Thank you.
Thank you very much.
Thank you, Professor Xia. So the forum is a success, and the time is limited, and the forum is over, finished. Thank everyone. Good afternoon, good morning, and good evening. The forum is over. Thank you.